So today we will talk a little bit more about what impacts the distance that the signal travels based on our knowledge about frequency shift keying properties. So in frequency shift keying, as we talked last time, we have center frequency, deviation, bitrate, and we also have crystal precision. So to describe all of that, we can go to frequency shift keying and look at what impacts the radio signal travel distance. So what is frequency shift keying range? So frequency shift keying switches between higher frequency and lower frequency, and the speed with which it switches between frequencies is the bit rate. So as we spoke last time, we have center frequency F0. We also have deviation. I'll copy the delta symbol from the internet. So it tells at what distance from center frequency is 1 bit and at what distance is the 0 bit. We also have bitrate. And from that, we could calculate Tx bandwidth, but we also have crystal precision. So I'll write it ppm crystal, and we also have Tx bandwidth. Which is the total width of our signal, and also Rx bandwidth. So, and in our picture that we usually draw when we talk about frequency shift keying, which is the widely used binary modulation, we have center frequency here. We have deviation, which corresponds to 1 bit and 0 bit. So this distance here is delta F. And this distance here also is delta F. And when we switch between ones and zeros, without really going through all of the math, it can be proven that bitrate is approximately equal to the width of each of these lobes. So this is the spectrum of our signal. It's symmetric. So to draw it correctly, it would be like this, roughly speaking. And the width of 90% energy, or 50% of energy, is bitrate. So the total width of our TX bandwidth is here. With orange, this distance is TX bandwidth of our signal. Right. So to calculate the total width of our signal, so that we know that our signal doesn't go outside of a permissible band, Tx bandwidth is calculated as 1/2 of bitrate plus 1 delta f plus another delta f plus another half of bitrate. So in total, it's 2 times delta f plus 1 bitrate. That is the transmission bandwidth estimate. But as we spoke last time, the frequency is obtained by multiplying crystal frequency by our multiplication factor through PLL. So for the base, we use, for example, 26 megahertz crystal, which we multiply, we scale it up using phase locked loop. For example, we multiply it 28 times and we get our 868 megahertz frequency. So since crystal is not exactly precise and its frequency drifts a little bit, a tiny bit, but we have to take it into account. It drifts a little bit higher or lower depending on the temperature and also depending on the crystal manufacturing precision. We need to assume the worst case scenario for the transmitter and receiver having shifted from the center frequency the most further away, guaranteed by the crystal. So for example, crystal ppm could be, for example, 20 ppm precision and another 15 ppm, for example, for over the temperature range. So the total Rx bandwidth to calculate the total Rx bandwidth, we need to imagine that the center frequency can shift by, and also this whole picture can shift by F center times ppm crystal precision plus ppm crystal temperature. So crystal has precision of plus minus 20 ppm and also plus minus, for example, 15 ppm over the temperature range. So you add these two together. And so, for example, we can have it in plus side, center frequency times the precision, and also to the minus side. It can also be, for example, in one end it is at room temperature, and in another direction it's, for example, very cold or very hot. So the same goes to the opposite side. So this can also shift to the opposite side by F0 times, oh, I can actually copy this thing. Also to this side. Oops. So, okay. Copying wasn't such a good thing. So F0 times ppm of crystal precision plus ppm crystal temperature. And they are given in crystal datasheet. So to calculate the total receiver bandwidth, we need to add also these numbers into account, because receiver needs to have so wide bandwidth to catch this signal, and also the signal drifted to one end or to the other end by the crystal precision. So Rx bandwidth is equal to Tx bandwidth plus F0 times ppm crystal precision plus ppm crystal temperature. Or in other words, it is equal to 2 times delta F plus bitrate plus F0 times ppm crystal precision plus ppm crystal temperature. So in our lab, we will actually calculate it on the whiteboard. When do we have lab? We have it next week on Tuesday from 10:15 to 11:50. So labs happen in school and the lectures happen remotely. This is so nothing really changes. Okay, so I hope you understand how to calculate radio frequency bandwidth. So when you design your own circuit, your own wireless system, you will be able to calculate these things. Okay. So next thing that we need to talk about is the impact of these properties to the range of signal. So I'll save it. Okay, I will call it frequency shifting parameters. And I will copy a little bit. Okay, so frequency shifting. And now let's talk about what impacts the distance that we can obtain with frequency shift keying. So our first parameter was center frequency. So how does the center frequency impact the range that we get? So as I mentioned before, a lower frequency travels through objects and walls better. Higher frequency is absorbed by objects better. So for example, 2.4 gigahertz or microwaves in general are very well absorbed by water. This is why microwave ovens exist. So microwave oven is just a device that radiates at 2.4 gigahertz frequency, and it just happens so that this frequency is absorbed very well by water. So you radiate these 2.4 gigahertz on water, and instead of just going through water and water doesn't absorb it and doesn't heat up, the opposite happens. Water absorbs these waves because they happen to resonate with water's molecules, and the waves don't go through water, but they stop at water and they heat the water up. They dissipate as heat inside the water. So this is why microwave ovens exist. And theoretically, you cannot really heat up For example, objects that are absolutely 100% dry, they wouldn't really heat up that well in microwave oven. But objects that have water inside, they absorb water with these 2.4 gigahertz very well. So it's absorbed, it doesn't go through, and it just heats up. This is why, for example, Wi-Fi signal doesn't really travel too far because, it, when it goes through human body, it actually is absorbed. And this is one of the reasons why you cannot really radiate too much energy in, for example, Wi-Fi. And this is the reason why microwave oven has a metal case around it, so that these infrared, sorry, not infrared, microwave waves don't travel outside and into human body and don't damage it. So Wi-Fi uses the frequency, but the maximum power that is allowed to radiate from Wi-Fi router is very small, very limited. It's just something like 0.1 watt. So it doesn't really do anything to a human body. And it is an available frequency band worldwide. So higher frequencies get absorbed by material more, so lower frequencies are better for range. But lower frequencies can carry uh, only slower information. So low frequency means that you have lower bitrate as well. But bitrate is like a little bit separate topic. So right now talking about frequency, lower frequency is higher range. So to put it in simple words, lower frequency means higher range, but lower speeds. So if you're building some simple wireless communication that only reports some situation once a day, you don't really care about high speeds, so you want higher range, so you would select a lower center frequency. And this is why, for example, originally cellular networks that are used in cell phones, they used, generally speaking, these bands. They used 800 megahertz, 900 megahertz, 1700 megahertz, and sorry, 1900, I think, and 2100 megahertz. I guess these were the bands. So now for these new CAT M M1 and NB-IoT version 1 and 2, they are actually starting to look at lower frequencies, for example, 450 megahertz for bigger range. So even though we would think that 4G and 5G technology would be all about speed, but for these embedded devices, lower frequencies are all actually better. So let's go and check out on the internet NB-IoT, narrowband IoT. What's the frequency? Center frequency, do we have it here? Probably not, but let's go to tell it ME31. So here it is. For example, if you want to build a device that uses cellular network for wireless data transmission, you can buy these modules, and somewhere here It will also tell the frequencies at which it transmits. So for example, this G1 object. It has the bands, but where are the frequencies? I checked it out yesterday and cannot really see them anymore. So basically it says 4G bands. So as you can see, there's a lot of frequency bands for LTE. And here it is. So 451 to 456. Subset of bands. So for professional mobile radios, it's used to transmit data and information, and it will have higher range. So, so lower frequency means higher range, but lower speeds. So it cannot be used for example, internet, because that internet connection would be really slow. But for simple wireless network that only rarely sends data, it's perfectly fine. So the next thing is deviation. So what is the impact of deviation on the range? So the idea is the bigger the deviation you have, you would think it's better because ones and zeros are further away from each other, so it would be easier to distinguish them. So for example, we have center frequency and deviation. So you would think that increasing this distance between zeros and ones would mean that you get a higher range because zeros and ones are further away. For example, if ones and zeros, I'll draw a small picture here. If ones and zeros are side by side with very little distance, then of course, looking from far away, it seems like it's only one peak. You can't really see that there's two different peaks. So putting ones and zeros further away would mean higher range. However, if you put ones and zeros very far away, if deviation is very large, then the problem appears that the receiver receives not only ones and zeros, but also all of the noise that is between ones and zeros. So of course, when you send a signal over large distances, there's also some kind of noise in between. For example, there's some lightning strike or some other senders and receivers with some harmonics. So there's also some noise that puts on top of these signals. So if you put 0 and 1 very far away, the problem is that there's a lot of noise in between. So actually the quality of link goes down. So having a large deviation means zeros and ones are far away, so they would be easy to distinguish, but also there's large noise that goes into receiver and damages the signal. But putting ones and zeros very close together means there's almost no noise going into the receiver, but ones and zeros are so close together that it's hard to distinguish them. So for deviation, the truth lies somewhere in the middle. So it is recommended that deviation is actually moderate. or average or just, decent deviation is the best. Not too big, not too small. So recommendation is to set deviation approximately equal to 2 times bitrate to 1/2 bitrate. So we will use a new name, modulation index H, and H, this modulation index, basically is an index that tells you what is the ratio between deviation and bitrate. So it is expressed as 2 times delta F divided by bitrate. And the recommendation is that H is 0.5 to 2. So for example, many choose just modulation index equal to 1. So, so what does it mean that H is equal to 1? So at H equals 0.5, 2 delta F's divided by bitrate is 0.5. So it means 0.5, 1/2, 4 times, let's see. So 1/2 is 2 times delta F divided by bitrate. So it is bitrate equals to 4 times delta F, or delta F is bitrate divided by 4. And modulation index 1, so I'll continue here. So delta F equals to bitrate divided by 4. And in the same manner, if modulation index, let's say we decide that our modulation index will be equal to 1, deviation is equal to bitrate divided by 2, and at modulation index H equal to 2, delta F is equal to bitrate. Right? These are just popular options. Nobody really goes lower or higher. Most people just choose modulation index equals to 1, you know. So basically, deviation should be chosen based on the bitrate that we want. If we want to send bits very fast, we select high bitrate, and also the deviation will increase correspondingly. And if you want slow bitrate, then deviation will also be lower. So deviation, increasing it or decreasing it at random does not tell you very much about the impact on the range. Deviation should be calculated based on your bitrate. Okay, so next property that the frequency shift keying has is deviation is bitrate. So bitrate. So this is 1, this is 2, and this is 3 bitrate. So what is the impact of bitrate? So if you change between ones and zeros very fast, then if we are very far away from the transmitter and there's a lot of noise over the signals, there's a lot of noise, then the longer each bit is transmitted, the easier it is for receiver to receive it correctly. So if they switch very quickly and there's a lot of noise on top of the signals, which is the case in the world, in the real world. So if they switch very quickly, then it's harder for receiver to correctly receive bits and the range will be lower. So low speed means higher range and higher speed means lower range. Higher speed means lower range. This is why actually, for example, 2.4 gigahertz Wi-Fi can be configured to run at relatively low speeds and you'll get higher range. But this new 5 gigahertz Wi-Fi, well, first of all, its center frequency is higher, so it's absorbed by objects better, but also its speed is significantly increased up to 1 gigabit per second theoretically. So the bits change so quickly that when you're nearby, you can distinguish them very well. But if you go further and further away and they get more and more silent, more and more similar to noise, it becomes very quickly impossible to hear ones and zeros under the noise. So as a result, 5 gigahertz Wi-Fi only works in like the same room, or maybe the room and the room that is next to the router's room. So the range is very, very low. So 5G, 5 gigahertz Wi-Fi seems to be a future, but very small range future. So if we increase the speed, bits change so fast that ones and zeros are harder to distinguish and it's hard to receive the signal correctly. So higher speed means lower range. All right. So, and the fourth parameter that we have, ppm of crystal. So generally, if you select a more precise crystal, it means that it will drift away from center frequency to lesser extent. Maybe instead of drifting 20 times center frequency, it will only drift, for example, 5 times the center frequency. 5 ppm times center frequency. So initially the crystal doesn't really change the range, but it allows you, more precise crystal allows you to select a narrower receiver band so that less noise gets into the receiver and you are able to hear ones and zeros, the good signal, better because you have less noise from the sides. So the impact of crystal precision is that lower ppm allows narrower Rx bandwidth, improving range. So if you select a more precise crystal, you can automatically the radio frequency receiver's bandwidth can be reduced to match the TX bandwidth better. So you will receive more of the good signal and less of the bad noise. So this is what you have to kind of remember. So for example, 2G cellular network uses low frequency, low bitrate, and very precise crystals to obtain a very high range. Okay, so I will save this picture and I will call it FSK range. Okay. So do you have some questions? You can type them in the chat box. Okay, and now let's talk about data transmission in the packets. So in general, the computer networks need to be organized somehow, and they are organized in layers or in blocks, and each block is responsible for certain task. Historically, at least for some brief time, the ISO model was used. It is used for internet connectivity to the fullest, but there's a lot of deviation from it. But generally, it is used. Let's see, I'll share the screen. So this OSI model, Open Systems Interconnection Model, is a conceptual model that characterizes and standardizes communication functions of some network. It is a general idea, and many networks use at least some part of this model. The internet protocol, for example, the browser uses all of these layers, but many wireless networks only use some. For example, all networks use physical net layer to send the signal, data link layer to send data frames. In others use also network layer, transport layer, session layer, presentation, and application layer. So we will just briefly look at how to organize the wireless networks in such way that, you know, we don't get overly confused with how to run the network and how to organize it, so that everything is not in one big pot, which we don't really understand how to manage. So let's look at this OSI model, you know, from a general perspective. So the layer architecture is the following. We have some lowest layers, which are called media layers, and they are generally used to just send some arbitrary data in some sort. And then there are host layers, which are more like application or API layers. And let's look at them. So the lowest level is physical layer, which describes how we send actual signal. For example, do we use a cable or do we use wireless? If we use wireless, what frequency should we use? Should we use 2.4 gigahertz or 5 gigahertz? How long should we send each bit? Do we use frequency shifting, or maybe we use orthogonal OFDM frequency modulation, or something like that? Or maybe we use optical cables. So physical layer of a network describes the physical connection between computers. And for example, the thing that we are using right now for this video lecture actually uses multiple physical layers. For example, my computer is connected to Wi-Fi router through Wi-Fi, but the router is connected to the internet with a cable, right? And this is why Wi-Fi is a separate branch of internet developed by separate group of people, and cable internet, which is, you know, internet service providers and everything else, it's like a separate thing. So you cannot just directly take Wi-Fi bits and send them over the cable. Wi-Fi is different. Wi-Fi needs different error correction and detection algorithms. Wi-Fi is less reliable, so you need more error checking, whereas cable connection is more reliable. You need less connect, error detection and more speed and so on. So Wi-Fi is one standard, and for example, Ethernet, which is cable connection, is a different standard with different properties. So this physical layer, for example, Bluetooth physical layer describes how Bluetooth signal is transmitted. Let's check out, for example, Bluetooth modulation. So for example, Bluetooth modulation, originally it used Gaussian frequency shift keying. For example, Wi-Fi signal uses OFDM spread spectrum modulations, so they're not compatible directly. So here is phase shift keying, differential quadrature phase shift keying for later versions, and Bluetooth low energy use, I think, even a different way of sending bits, right? So, okay, let's go through all of these layers in general, and then we will start to study about each layer and its tasks further. So physical layer is the agreement of how we send the signal. Next layer is data link layer, and it is the first layer that deals with the actual data, the packets. And these packets are actually not called packets, but they are called frames. So for example, I want to send data from my computer to your computer, and the data is divided into frames which travel from my computer to the Wi-Fi router. And these will be Wi-Fi frames. And frames travel only from one device to the next device that is directly next to it. For example, the frame travels from my computer to my Wi-Fi router, but it does not travel to your computer because the frame needs to be received by Wi-Fi router, and it needs to be checked for errors. And if I want to send it over the internet to another computer, this frame will be translated into cable internet's or Ethernet protocol and send over Ethernet's physical layer. So data link is between two devices directly, and it travels from one device to the neighboring device. Okay, so I'm connected to my Wi-Fi router, and the Wi-Fi frames travel from my computer to Wi-Fi router where they are checked for errors. If I had an internet connection with a cable, then the frame would be sent over Ethernet cable connection to the router or to my internet service provider if I have direct connection. But the frames are between two devices. So here is the definition. It's a reliable transmission of data frames between two nodes connected by the physical layer. So frames are sent also from your cell phone to the tower. If you want to connect to internet using your cell phone, the frames from tower are then translated into Ethernet frames and sent to your destination in the internet. Next layer is layer number 3, which is called network layer. Its data is called packet, and the network layer has the main task of routing your packets. Okay, so network layer deals with routing. Data link layer doesn't have any routing because it sends the messages from one device to direct uh, distance devices, direct connected devices. So network layer is the layer that deals with routing. So for example, network layer, let's say I want to connect to Riga Technical University server, and the network layer is the layer that needs to find Riga Technical University servers on the internet. Okay. And we will study about how it's done. It's actually, if you study it, it's not really that complicated. But this is why we have routers which exchange information between one another. They have routing tables which they exchange so that my router can actually quickly find to which router to forward the messages if I want to connect to Riga Technical University server. If it doesn't know, it just asks its neighboring routers. If they don't know, they ask the next routers. So the path can be found pretty quickly. Next layer is transport layer, which deals with reliable transmission of data segments between points on network, and it includes segmentation, acknowledgement, and multiplexing. Well, we're not going to really look at multiplexing, but segmentation and acknowledgement. So transport layer is the one that uh, that creates reliable transmission. So this layer has to deal with the cases where, for example, I'm connecting to Riga Technical University, and during the connection, for example, one of the routers in the path loses power, it just switches off or restarts. So some information in the network layer can accidentally be lost because, for example, the cable was disconnected for a short period of time, or electricity disappeared, there was power outage for a brief moment, or somebody accidentally restarted the router somewhere in some server. So in network layer, it can find path, but it can also lose packets. So this transport layer needs to follow through all of these packets that they really are sent and received in the correct order. And if they did not arrive in correct order, then it manages retransmission. And if they arrived at correct order, they deal with acknowledgement. So if they receive the message, they send acknowledgement. Thank you for the message. And as you can see, if, for example, we tried to make all of these functions into a physical layer, or for example, data link layer, our network would be very, very hard to manage, and it would be very hard to find some mistakes. So this is why it's been separated. Data link layer does not manage reliable transmission. It only sends messages from one device to another. It can implement acknowledgements, but it's not a mandatory requirement, right? Network layer, the same. It only does routing. Transport layer only provides reliable transmission between points on network. So the next layers are kind of hard to describe. For example, session layer manages communication sessions, continuous exchange of information in the form of multiple back and forth transmissions between two nodes. This session layer is often just implemented as a part of just 5, 6, and 7 layer combination. So, but it deals with sockets, it opens a connection or closes it and tells the other end that the communication has ended. So that would be a session. It would, it would do connect and disconnect tasks. Next is presentation layer, which should deal with encryption, decryption, and data compression. Because as it turns out, a lot of information can be sent compressed, and that way it occupies less of the internet resources. So oftentimes many, for example, texts compress very well, pictures also compress very well. So some data can also be compressed, but mainly presentation layers should be concerned with encryption, decryption. And this is what you have to kind of realize, that at any case, you should not rely on encryption of, for example, physical layer that, for example, nobody knows your center frequency. Actually, using some frequency sniffers, it's easy to find out what your physical layer's frequency is, so it will soon not be any secret. Data link layer is concerned with frame transmission, and it does not usually do encryption for various reasons, but one of them is that, let's say we create a router with some encryption in it. And it turns out that this encryption method is not safe. There is some error. It's oftentimes very hard to update this data link layer. Or if the device is already compromised, you cannot, for example, do that. So data link layer is more for speed and not really for security. For network, also the same. It can encrypt messages, but it's not really required. For example, Wi-Fi routers in data link layer, they do encryption because signal is sent over the air where everybody can hear it. But for example, cable internet usually does not do encryption because it's not that easy to break into the house and cut the wire and connect in between and listen to the packets. And even if it were the case, encryption might not really be helpful there. So always the application should do the encryption anyway and should not rely on the lower layers. Because, for example, maybe somebody has an old router which doesn't use any encryption at all, right? Maybe, transport layer doesn't have to deal with encryption and network layer neither, because encryption can only slow it down. So all data should be encrypted at the highest level, and you should not rely that lower levels will present encryption. And the highest level is application level, where you basically send and receive the final data and use it. high-level application programming interface, including resource sharing and remote file access. Let's see. So it is something that is closest to user. So user just says connect to the internet, and all of the encryption and data transmission is done by lower levels. So usually these presentation, session, transport, network, data link, and physical layers, all of these layers should be managed by operating system, and the user only uses the highest level API, where he says, for example, HTTPS or TUS RTULV. I'm telling operating system or browser that I want to go to this website using this HTTPS protocol, and everything is done here. So the data link was done by my Wi-Fi card, and the physical link network layer was done by operating system and the router. Transport layer was also done by router. Session was done by my operating system. Presentation, encryption, and decryption was partly done by, I think it was done by browser. Browsers do the encryption. If you try to connect to non-encrypted web page, it will give you a warning or maybe even an error. And this highest level API was kind of like what I did. So, and partly the computer operating system and browser. So as you can see, browser does the encryption, and it does not rely on me connecting to, for example, secure Wi-Fi router, because browser doesn't know if I'm connected to a new router or old router. So it does entire web page encryption and decryption, so that even if I use non-secure router, my data is still private. Nobody can read, what the contents of the page are. If we look at this OSI model, for example, the fact that I request connection to Riga Technical University server is visible to hackers because it is in this network layer. And if somebody breaks into my home network or connects to my cable, well, they see that my computer is requesting routing to Riga Technical University server. So we can actually see where I'm connecting to. My internet service provider actually sees what websites I visit, because my computer cannot encrypt that information, because the routers need to know what web page I'm requesting. If I send them encrypted name of the website, they would know what website I'm trying to connect. So this information that I'm connecting to Riga Technical University is generally visible to the internet. Routers need to know it, right? But when I connect to Riga Technical University, the web browser and Riga Technical University server generate an encryption key. We exchange it in secret way over unsecure connection, but the algorithms have been developed so good that even though we use unreliable compromised network, the network keys cannot be obtained by a third party. And after we have created session keys, we encrypt the web page and the server sends me this information, but it's encrypted, so nobody really sees the content of my web page. Only my browser receives encrypted data, it decrypts it, and displays this web page as is. So we will also study about encryption, and I will show you some algorithms that are used for encryption in such way that even though you exchange data over bad connection, which is visible to others, it is possible to exchange keys in such way that even though everybody sees the keys, they cannot decrypt the messages. It is called uh, asymmetric encryption, or it's also called public key cryptography. So even though you send the password visible to everybody, nobody can use it because you actually send half of your password in such way that it can be used for encryption, but to decrypt information you need the other half, which you didn't send, and you can use it to decrypt and get the data, but nobody really sees what you're doing. We will talk about it in further lessons. So if we subdivide our internet connection or wireless sensor network connection into these layers, it's just much easier to manage all of this. Otherwise, it's just way too many functions on a single layer of network. So if we subdivide it, we can manage it and understand it much better. Okay. So we talked about physical layer in our lesson when we talked about center frequency and bit rate and how long each bit is being sent and what the deviation is. That would be our physical layer. And the next thing that we are going to talk about is going to be data link layer, or how to send data between two devices that are connected together, either through a cable or through wireless. So we will look at this data link layer. So and let's start with the concept, which is really good at wireless sensor networks. So in wireless sensor networks, for example, we have some router and we have several computers that are nearby next to each other. So in wireless networks, you need to remember that all devices can hear any other device. Sometimes if they're on the opposite side of the router, for example, they don't hear each other, but they hear router. So generally, let's make a small wireless sensor network which will have the following nodes. It will have A, B, C, and also D. And let's say we have a moderate range. So when we have these devices in data link layer, A can hear B and B can also hear A. Let's say that they're, the symmetrical communication. B also can hear D and vice versa. A can hear D and vice versa. And B can hear C and vice versa. Okay, so it works in Wi-Fi. It also works in some cable networks very similarly. If it's, for example, Ethernet, then all of them are connected to the same cable pair. And since we don't know and how all of these devices will be deployed, and for example, maybe C device can move around the house, for example, it's a wristwatch or something like that, it can happen that C, for example, moves here, and now all of the devices hear each other, okay? This means that the devices should have some unique ID so that everybody knows and can address every other device. So C now is connected to every device, and A and B and B also. So we have this network where all devices are connected to each other. So in data link layer, we have a new term, which is called media access code. I think that's the name. Let's see. Okay, a lot about Macintosh computer. MAC address. Media access control. Sorry, media access control code. Um, So since we don't know how these nodes appear in the network, each of the nodes should have some unique ID, some unique number, so that if D wants to communicate with B, well, we need to be sure that there are no two nodes with name B at the same network. Otherwise, both of them will think that the message is for them. So each node should have a different name. And for this, we use MAC addresses. And for example, every network card has a unique MAC address, which does not repeat. And for example, MAC address for Internet Protocol is 48 bits long, random ones and zeros. And they are distributed centrally. And it happens in the following way. You have 6-byte long address, and you can buy the top 3 bytes and then use the lower 3 bytes in whatever manner you want. Just make sure that each device has a separate and different MAC address. So the first 3 bytes is organizationally unique identifier. And you can buy MAC address from the internet. And it costs approximately 1,500 euros to buy one code, and you have 2 to the power of 24 different MAC addresses when you buy them. So if we select scientific calculator, 3 times 8 bytes is 24 bytes. 2 to the power of 24 we need to calculate. So you can buy 16,000 million MAC addresses for 1,500 euros approximately. And then you can use these MAC addresses to build network cards, and you will be sure that no other card has the same MAC address as your network card. If you make your own wireless network, you don't have to buy these codes. You just have to make sure that your devices also have unique IDs. So every device has to have a unique ID or different name, as in this picture. This device has name A, this is B, this is C, this is D. And so when A says, I want to send message to D, then only D responds, and B and C see that it's not for them and don't respond to the message. So this unique name of each device is called MAC address. If you build devices for internet connection, you need to buy them. But if you make your own personal proprietary networks, which do not connect to internet directly, then you can use your own numbering system. So if we want to, let's say, node A, so these objects are called nodes. So these are nodes. How can I select some big color of this? So these things are called nodes. This terminology. And let's say that node A wants to talk to node D. Just send some data in the data link layer. How can we do it? We can come up with our secret protocol, but since all of these devices will hear the message, obviously inside the message we need to say the destination. We need to say who is the sender, and probably we also need to add some length so that the receiver knows how many bytes it will receive. So let's try to go through with all of this. Let's say we want to make a message, and what would be the contents of the message? Oftentimes the message starts with the length. For example, 1 byte is the length of the message. If you know that your messages can be long, you can also define it as several bytes. Then we want to tell who do we want to send this message to. For example, A wants to send to D, so we need to put some destination address inside our data frame. Also, so that the receiver knows who sent the message, we also need to put our own name in the message. So it will be source part of the message, of the frame. Oops. So I'll move it down a little bit. Length, destination, source, and then we add payload. Payload is the data that we want to send. You know, for example, we want to send the temperature of node A to node D. So we calculate the length of the message and put in the beginning. Then we send destination address. Then we send source address. Then we send the temperature, for example. Okay. And then there are several popular fields that are also added to the frame. For example, frame counter. Let's say a node A sends a message to node D, the temperature, and after some time, it sends the same temperature. The temperature didn't change. So how can D know that the message received is a new packet and not a new frame and not the same old frame that is just retransmitted? So if we want to, we can insert a new field in our frame, which is a simple counter. We will call it frame counter. How can we add it? Something like this. Okay, so frame counter is here. And what other fields might we want to add to our data link message? If we want to, we can also add some check, some method to check that there are no bit errors. For example, we send this message, but at the same time when we sent it, there was a lightning strike which caused some electromagnetic noise and some bits were changed inside of this message. So we want also to add at the end some kind of error checking mechanism. For example, the sum of all bits, how many bits we send, how many ones we send, or something like that. I'm going to put at the end CRC, which is short for cyclic redundancy check, but there are several algorithms that we can use. Let's see, for example, Ethernet data frame format. Well, let's look at a real world example, how data frames are sent over Ethernet. Well, as you can see here, they have something called preamble, then SFD, destination address, source address, length, data, and also checksum, error catching code. So very similar to what I showed you here, for example. Okay, Ethernet frame. What is preamble? Uh, Start frame delimiter. So when sending information over Ethernet, before sending data, it sends some ones and zeros. And the reason is very simple. Ethernet cables are very long. So when a computer on one end starts to send, it's possible that a computer on another end of the cable started to send at the same time, and there would be bit collision on the line. So Ethernet signal first sends 7 times 8 bits of special code, and it listens if what it sends is the same as it receives. And if it is, it means no other computer is also sending at the same time. So the network card can go on and send also the start of frame, destination. You see MAC address destination, 6 bytes, MAC address. The source MAC address, 6 bytes, then some tag, length, 2 octets. It means that the maximum length would be 64 kilobytes, but in reality, the maximum payload is only 1,500 bytes. And 32-bit CRC, and then a pause, interpacket gap, which is basically silence for 12 times 8 bytes so that the receiver can manage this packet after receiving, so that the sender doesn't send 1 million packets in row and the receiver is just overwhelmed by the amount of information. Okay? So this is very close to what I draw here, except I added this frame counter. It's not mandatory, but it just oftentimes helps the wireless transmission networks to see that this is a new frame and not the old frame from retransmission. Let's see what is Wi-Fi frame, for example. Wi-Fi frame. Okay, so frame control, address. There are several addresses. Let's see. Maybe there's a better example. Okay, so generally it sends frame control, which tells you what the frame type is, duration ID. Then it sends source address, destination address. I think other addresses are not used, but you can check it on the internet. Then some other control bytes, and then the frame body, which is basically the payload, and then FCS, frame check sequence. So it's an error detecting code. It's similar to checksum, but maybe it uses a different algorithm to calculate. So this is how data is sent over data link layer in frames. All of them have length, destination, and source address and payload. And most of them also have error detection code so that the receiver knows if there are some bit errors. And we will make such example frame format in our lab when we meet in lab and we do some more programming. Okay, so I guess the next time we meet is next week in lab. So if you have some questions, type them in the chat. Otherwise, that's all for today. So do you have some questions? Okay, great. Then we can finish today's lecture, and I see you next week.